Hello everyone. Today in this lecture we are going to discuss regulator design by two methods. Okay, which we usually find in the practice. Okay, and a regulator design, it is, here is the reference, it is realized in a feedback configuration where error signal is fed as input to the regulator here, which provides the input into the plant, G of S here, and there is a measurement going back that is actually checked against the reference value, such that error signal is that marker that shows whether a reference is identical to the output of the system. In other words, the configuration that this is U of S, the configuration that we are looking at is essentially configuration that takes into account the measurement, the feedback configuration takes into account the measurement from the output, and that measurement from the output is taken, is compared with the reference, and error is provided, which goes into a controller. One can also have the configuration that adds here additional feedback element H, and again, a regulator design is nothing but to find the H, to find the C of S transfer function. So find the C of S such that closed loop transfer function is stable. PCL is stable, or that the poles of the closed loop transfer function are negative. Okay, so having this in mind, one can easily see that there are two available methods. First is just gain-based regulator or controller synthesis, where C of S is just a gain element, simple gain element. And the second one is dynamics based regulator synthesis, where C of S is given by some transfer function and C of S, which also has to be proper or strictly proper. Okay. And we will discuss both of these methods in our lectures. And in the first, we just claim that in general, simple gain feedback can be utilized to stabilize the system and to ensure the closed loop system stability. Plus minus this error signal UofS, and this is YFS. And constant gain is synthesis is find the k. Find the k such that closed loop polynomial P of s, which in this case of G of s being just n of s d of s, is nothing but d of s plus k n of s. Okay, closed loop system characteristic polynomial. I want to circle that. This is also denominator of the closed loop transfer function in this system, because if we just write the closed loop transfer function, it will be G closed loop of S K G of S divided by 1 plus K G of S, and since this is n of s, this will be K n of s. Here we'll have d of s plus k n of s. In this formulation, we assume that n of s and d of s are co-primes. So n of s and d of s co-primes. Co-prime polynomials. In other words, they don't have common factors. Do not have common factors. Okay, that's very important. And in this particular way, the finding of k has to assure that there is a range of k such that the closed loop system is stable. In other words, for fixed k, the closed loop characteristic polynomial will have a certain poles. So this is imaginary, this is real, okay? And for the k, for example, equals 0, the closed loop polynomials will be, let's say, this one, for k equals 0. So as k varies, k goes from 0, let's say infinity, okay, these poles will start changing slowly. For example, in this way. Will start changing this way. And at some critical k critical, kc, the poles will cross here from being stable to unstable. Unstable poles of the closed loop characteristic equation. In other words, the operating K is just going to be K from K0 to K critical. This is the operating K. That's the domain of K that will stabilize the closed loop system. Let's look quickly for the example of this. So example is a given as the system that has the following transfer function. This is R set K gain here plus minus, and the transfer function of the system is 4s plus 1 divided by s squared minus 2s plus 3. We see that system in the open loop without feedback is unstable because this term minus 2 is negative, so polynomial definitely has a unstable pole. Okay, so characteristic equation pi of s in this case is going to be s squared minus 2s plus 3 plus, put this in brackets, this is our d of s, you're recognizing this, so our d of s plus k multiplies 4s plus 1, this is our n of s. Okay. And after rewriting this equation and factoring everything, is s squared plus 4k minus 2s plus k plus 3 equals 0. So, to ensure that closed loop characteristic polynomial has a negative poles, one has to ensure, because we have a quadratic formula for the x squared plus x plus c. From quadratic formula we have that x1, 2 is going to be equal minus b plus minus b squared minus 4c. A is 1 in this case by 2. So we have to have that 4k minus 2, okay, has to be greater than 0. And also we need to ensure that k plus 3 is greater than 0. K plus 3 is greater than 0. This yields that k is greater than 1 by half, and the k is greater than minus 3, okay, which if we place the k, for k greater than 1 by half, we have 1 by half, because all k's which are taking 1 by half, okay, and k greater than minus 3 are all of that. So where this is minus 3. So finally we obtain that k has to be domain of k, stabilizing k, is going to be from 1 by half to plus infinity. Okay? This is our solution. Those are the gains, stabilizing gains here, that completely ensure the stability of this system. Okay? One can observe that for k equal 1 by half, here is just remark, if we place k equal 1 by half, okay, then P of s will become s squared plus 3 plus 1 by half equals 0. In other words, in this case, this is with the moment at which k we will have a j, the closed loop poles are going to be pure conjugate complex values, 3 plus 1 half and minus j 3 plus 1 half. This is the moment where the gain will shift the closed loop characteristic polynomial poles from stable into unstable limit. Okay, we see that the regulator synthesis with a simple gain is very easily done, and it can be easily calculated if there is a stabilizing gain. Okay, we will also demonstrate another synthesis where we design dynamical control, and that is the case when K cannot stabilize the closed loop system.